This video is going to cover how to solve trig equations. Okay? So our job for each of these is going to be solve the equation and give all solutions from 0 to 2 pi, or in the unit circle. And then we're going to go and find the general solution, so every solution after that. Okay? For ones that don't come out nicely, we're going to round to the nearest hundredth then. So our first one, we've got sine of theta equals the square root of 2 over 2. Hopefully by now you are familiar with seeing those numbers. Okay, we want to see if the square root of 2 over 2 would appear on a triangle. Okay, the square root of 2 we know appears on the special right triangle 45, 45 because we've got opposite over hypotenuse 1 over the square root of 2, but that rationalizes to be the square root of 2 over 2. So we're going to have the 45, 45 be the triangle we need. We just have to decide what quadrants we could be in. Okay, so we've got positive, so sine is positive in the first quadrant and in the second quadrant. So I'm going to draw two separate triangles in each of those. And then, since I know it's a 45, 45, I don't really need to label my sides, I just need to know those reference angles. Now, since our interval is from 0 to 2 pi, I'm going to call this 45 degrees pi over 4 in radians. Now, to decide what this is, you might want to think of it in degrees. Okay, we know that from here all the way over is 135 degrees, but again, we need it to be in radians, so you can take that 135 and change it to radians, divide by 180 and tack on a pi. And that's 3/4 pi. Or, what I like to do here is I know that this straight across distance is pi, and I know that this reference angle is pi over 4. So it's 1 minus 1/4 pi or 3/4 pi. You get to the same thing, just kind of thinking of it in a different method. Okay, so I've got two general solutions here. My pi over 4 and my 3 pi over 4, I just have to generalize that now. Okay, so I'm going to write theta equals, and I'll group them since we've got two different ones, pi over 4 for the first one, and 3 pi over 4 for the second one. Those are my two solutions. Okay, but I want to say every solution after that as well. Okay, this is kind of using the periodicity theorem. Okay, I know that here pi over 4 is the solution, but if I go another time around the circle, or 2 pi more, I'll get to another solution in the exact same place. So I'm going to add on the period 2 pi, but I want to do this any number of times. Okay, so I'll say 2 pi n. Same thing goes for the bottom one, plus 2 pi n. We just have to make sure that n is an integer. And that takes care of every possible solution, or every possible theta, that has a sign of radical 2 over 2. Alright, the next one, we're looking at cosine this time, and cosine is positive in the first quadrant or in the fourth quadrant. Okay, the difference here, though, is 1 and 3. I don't have a special right triangle that has those numbers on there. Okay, but I'm trying to solve for theta still, so I can find theta by using the inverse cosine of 1/3. Now, I know that this isn't a special right triangle, so that means I don't expect to get a answer that looks very nice. So inverse cosine of 1/3. So approximately 1.23. Now I'm going to show you what mode I'm in here is radians. Okay, and normally we're not used to using radians when we find the inverse. Okay, but in this case we wanted our answer in radians because we wanted it from 0 to 2 pi. Okay, so if you didn't get that answer, change your mode over to radians and do it again. Okay, we've got approximately 1.23. That's my angle in this triangle here. So we just have to decide, well, what would this one have to be then? Okay, it might be easier to think of this if we had degrees, and I'm just going to make up a degree value. If I had a triangle here and here, let's call it a 30 because that's nice to work with. If my first answer was 30, I would get my second answer pretty easily by knowing that all the way around the circle is 360, but I want 30 less than that. So 330 would be the theta down here. We can apply that to what's going on here. All the way around the circle is 2 pi in radians. I just need to subtract my angle measure from that. Okay, so 2 pi minus that 1.23. Approximately 5.05. So those are my two angle measures. I just have to group them together. Notice I put approximately here because they're not exact. And then I want every other time again around the circle. So I'm going to add the period of cosine, which is plus 2 pi to both of them. And then an infinite time around, so multiplied by n, where n is an integer. Okay, so when it's not exact, when the numbers in your fraction or whatever your number you're working with isn't from the sides of a triangle that you know, then you're just going to use the inverse function on your calculator to solve. Now, the next one's a little different because we're not saying that sine is equal to some number. We're saying sine is equal to cosine. Okay, so we're going to think about which quadrants sine and cosine have the same SIG in sine. Okay, if we start with that, I know that they're both positive in the first quadrant and they're both negative in the second quadrant. So I'm looking for a triangle in either the first or the third quadrant. And then I just have to figure out where my sine and my cosine are the same. Well, on a triangle in the unit circle, remember that sine is your vertical distance and cosine is your horizontal. So if those are the same, we have an isosceles triangle, which we know is our 45-45 triangle. That being the case, my first theta solution is pi over 4 because of the 45 degrees. Now, whichever you prefer, you can either go find it in degrees, okay, or think of this as pi, or 1 pi if that helps, and then I need 1/4 more. Okay, for me that's 4/4 plus 1/4. Down here I should have 5 over 4 pi, or 5/4 pi. Now, this time I have two solutions, okay, but there's something special about my solutions on my picture here. If you notice, they are actually the same distance away. From my first solution to my second solution, it's 180 degrees. And then from that second solution back to the first, it's still 180 degrees. And I can go in that same pattern forever and ever. So instead of having to write out both of my solutions and add 2 pi to it each time, I can actually only look at my first solution, pi over 4, and add pi every single time. Get to that one, back up to the first one, as many times as I want, so times n, as long as n is an integer. So this time I've got one smooth equation to get all possible solutions here. Okay, anytime there's a pattern where there's an equal distance between all of the solutions, you want to see if you can see what that distance is. That allows us to simplify our equation, and it goes so that we're not repeating ourselves and hitting the same solution more than once. On the next one, there's a couple different things going on. Okay, first of all, tangent is not by itself, and second, tangent is being squared here. Okay, so just like when solving normal equations, we want to get tangent by itself by dividing by 3 first. And then we need to get rid of that squared. Okay, just like with x squared, we get to take the square root of both sides, and then I've got tangent theta equals, every time you take the square root, you've got 2 answers, so plus or minus. The square root of 1 is 1. The square root of 3 is simply the square root of 3. Now, I'm going to recommend that you do not rationalize this because it will help us draw our triangle. Okay, the square root of 3 and 1 show up on a 30, 60, 90 triangle. Okay, so I need to figure out what quadrants I could be in. For tangent, we've got plus or minus, so that means I could be in any quadrant I wanted to be. And then, tangent is opposite over adjacent. Let me pause here while I fix my pen. That looks a little bit better. Okay, so my opposite side on my triangle is 1, and my adjacent is the square root of 3. Since my opposite side is 1, then my reference angle is 30 degrees. Okay, and I'm going to go take a look up here. 30 degrees is pi over 6 in radians. Okay, then here, remember this is pi straight across, and if I want pi over 6 less than that, that's just 1 minus 1/6, or 5/6 pi. Here it'd be 1 plus 1/6 here, 7/6 pi. On this one, we are 1/6 less than 2, so that's 11/6 pi. Now, if you notice, very similar to what we had over here, opposite points are the same distance away from each other. If I start at the first one, I can go find the other one by adding pi, and that continues the same process all the way around. That also works for my second solution over here in quadrant 2. I can add pi to get to my fourth, and I can add pi again to get back to the other. So there's a constant distance between at least my pairs of pi here. Okay, whereas if I went from every single solution, the distance from pi over 6 to your 5/6 pi is just 2/3, or 4/6 pi, whereas from this point to this point is 2/6 or 1/3. So it's not a constant distance between every single one, but there is a constant distance between the opposite ones. Okay, so I'm going to just look at my ones in the first 2 quadrants. I'll say theta equals pi over 6, and I can add pi on to get to this one down here any number of times. And I can start at 5/6 pi and add on pi to get down here any number of times. Now, another way at looking at this particular problem is this is a tangent function. And we know tangent has a period of only pi, so really it starts repeating itself after the first half of this unit circle. So for tangent problems, we can actually only look at the first and second quadrant if we wanted to, and then we'll always add the period times n, which in this case is pi times n. Okay, so both concepts work. Alright, we've got a 5 times sine equals 1. Okay, we want to get sine by itself by dividing by 5. 1 and 5 are not nice triangles, okay, but we can still draw them. Sine is positive in the first quadrant or the second quadrant. since it's not nice, we just need to go figure out what theta would be. Again, I'm going to keep my calculator in radians because that's what it wants solutions in. So the sine inverse of 1/5 here is about 0.2. Okay, but that is this solution here in radians. I need to still go find this one. Now this is where all this practice working with radians is going to help us here. I know that this distance, my reference angle, is still going to be 0.2. Okay, then I know that straight across is pi. I just need 0.2 less than that. So for sine, instead of taking 2 pi minus your first angle, we're going to take pi minus our first angle, so that 0.2. So about 2.94. Then again, any time around the circle after that is plus your period times n. So plus 2 pi n, as long as n is an integer. On the next one, we need to get sine by itself. First step is to move over that 1. Then we'll divide by 4. And lastly, we need to take the square root. Remember, when you take the square root, you've got plus or minus. Square root of 1 is 1. Square root of 4 is 2. Now, we've got plus or minus, so that means I could be in any of my 4 quadrants. See if you can figure out what reference triangle has the sides of 1 and 2. For this one, it's opposite over hypotenuse. So your opposite side is 1, and your hypotenuse is 2. This is a 30, 60, 90 triangle, 1, 2, and the square root of 3. So my reference angle, since it's across from the 1, has to be a 30 here. Well, that makes my first radian answer pi over 6. Okay, the toughest part for some of you on this will be finding the other radian measures, so pause the video and see if you can figure those out. You should have come up with 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay, very similar to the one we did with tangent. Here, we want to look at any patterns that we can. Okay, so first we'll check if there's a constant distance between all of them. Okay, so pi over 6 to 5 pi over 6 is 2/3. 5 pi over 6 to 7 pi over 6 is 1/3. So we're already not at a common distance. Okay, so we can stop thinking about that way. But across from each other, you see this straight line, there is a common distance of pi both ways around for each of my different pairs. So if I start at the first one, I can get to the third and back. If I start at the second one, I can get to the fourth and back. So I just need to list my first 2. Pi over 6, then 5 pi over 6. And add on, this time, half the way around, or pi. And that gets all of my possible solutions. Go ahead and pause the video and see if you can do number 7 completely on your own. On 7, we want to solve for cosine. We've got cosine theta equals 1/2. That's a nice triangle, we know. Cosine is positive in both the first and the fourth quadrant, so I'll draw my triangles there. And then cosine is adjacent over hypotenuse. So my adjacent side is 1, my hypotenuse is 2, and that makes my opposite side the square root of 3. If my opposite side is the square root of 3, that makes this a 60-degree reference angle, which makes my first solution pi over 3. To get this solution down here, I just need to look at 2 pi and subtract 1/3 from it, 2 minus 1/3. So we've got 5/3 pi down there. There's no equal distance between solutions. Notice they're not the same, so we cannot combine that into a pattern. So we will just list them separately. Our first one is pi over 3. Second one is 5/3 pi. And then I'm tacking on the period of cosine, 2 pi into each one. Now, the next one, got a little bit of typo here. Okay, the next one requires us to think back to when we had x squared. Suppose this was 2x squared equals x plus 3. When we saw that, we knew that we wanted everything on one side so that we could attempt to factor to solve. That's what we're going to do even with sine here. Okay, so I'm going to move the sine and the 3 over to my other side of the equation here. Okay, now to factor this, it's frowny face factoring, hard factoring. We have to take 2 times -3, and we get -6. We're looking for the factors of -6 that combine to be -1 or have a difference of 1. Okay, so that has to be the 2 and the 3, and then the sign of the middle term will always go with the larger number. Now, we're going to streamline this process. Easy factoring makes our life easy when our a value is 1. So if I wanted to think of this as easy factoring, I'd have to get rid of that too. But I'd have to do it for every single piece here. Okay, that's actually going to affect these factors. All I have to do is go and divide those by 2 as well. So then I've got new factors of 2 divided by 2 is 1, and we can just leave that as -3/2. Since it's easy factoring, it would be an x and an x in each first space, but we're talking about sine, so we've got a sine theta in the first slot of each, and then we just have to slip in our factors, +1 and -3/2. Now, normally for factoring, we'd want to fix this and call it 2 sine theta minus 3. But for us, we're trying to solve for theta, so this form is actually better. All we have to do is say sine theta equals, switch the sign, -1, and sine theta equals, switch the sign, 3/2. So think way back to the first day we introduced the unit circle, the original 4 points. Sine, or the y value, was -1 straight down. And theta, straight down, is 3/2 pi. Now, I'm hoping that we're getting to a point where we recognize this 3/2 as a problem, because that's saying sine theta is equal to 1.5. 1.5 is greater than 1. There's no triangle sine where the opposite side is greater than the hypotenuse. Okay, so we can't have this. That part doesn't exist. Okay, so that we can just get rid of, and we have one lone solution that works here. Okay, so theta equals 3/2 pi, and then any number of time after that, period of sine is 2 pi. Okay. I think you should be able to handle 9. Go ahead, pause the video and see if I'm right. Now, there was one slight issue here, which you may have gotten. We know that 1/4 is not going to be a triangle that we know. That's not the issue. Okay, we know that tangent is going to be negative in either the second or the fourth quadrant. But remember what I told you. For tangent, we only have to look at the top half because the period is pi. So really, I only care about this one. Okay, but the problem happens when we try to take the inverse here. Okay, if I take inverse tangent of negative 1/4, I get a negative number. Okay, because it's finding this angle here instead of the first one that I want. Okay, remember in our instructions at the very first part of the paper it said find the equations, or solve the equation on the interval from 0 to 2 pi. Okay, negative numbers are not from 0 to 2 pi. So if I just want to get down from here back to my other one, I just have to add pi to that. That gives me my positive solution, and then I get to add the period every single time after that. Okay, so 2.9 here, plus pi, my period of tangent, and after that. Alright, the next one is factoring. Okay, see if you can set this up so that we can solve it. Easy factoring, I'm just looking at the factors of -2. That gives me -1. The only factors of 2 are 2 and 1, and then I just have to put my sign of the middle term with the bigger number. So, in general here, I've got sine theta equals 2. And sine theta equals -1. Hopefully you see that this can't be a triangle. Hypotenuse cannot be smaller than my opposite side, so get rid of that one. Then we just have to decide where sine is -1. Okay, if you remember from the last problem, it's 3 pi over 2 straight down on the unit circle. So again, I've only got one solution, 3 pi over 2. And I want every solution after that plus 2 pi in. Okay, number 11, very similar as far as it being easy factoring, cosine theta in my first slot. Then I'm looking at the factors of -6, so I'm looking for a difference of 5. Okay, difference of 5 will be 1 and 6, and I need my negative to go with the bigger number. So, +1 and -6, from here, you know that's going to be cosine equals 6. Same concept, the adjacent side cannot be larger than the hypotenuse, get rid of it. And we just have to figure out, well, where's cosine -1? Okay, so unit circle, cosine is x values. It's -1 at pi. So theta equals pi plus 2 pi in after that. The next one is hard factoring, okay, but I want to see if you can remember that shortcut that I showed you. Hopefully you've figured out the first step at least, -2, and you're looking for a difference of 1. So 2, 1, and the positive middle term goes with the bigger number. But I want to call this easy factoring, so I want to call it cosine theta. In order to do that, though, I need to divide everything by 2. Okay, so I need to divide my factors by 2. That simplifies to 1. This one we're just going to call -1/2. So then, cosine theta equals -1, and cosine theta equals 1/2. Just switch your signs. So cosine is -1 at pi. We just saw that. Cosine is 1/2. Okay, we're going to have to draw a picture for that one. Okay, cosine is positive in the first or the fourth quadrant. And cosine is adjacent over hypotenuse. So the adjacent side is 1, hypotenuse is 2. That makes your opposite side the square root of 3, which hopefully you see that makes this a 60-degree reference angle. Now, if it's a 60-degree reference angle, then this is pi over 3, and this is pi over 3 shy of 2 pi. So 2 pi minus pi over 3, or 2 minus 1/3, is 5/3 pi. Now, for the benefit of looking for patterns, I'm going to go ahead and draw this solution on as well. And if you notice, there's a constant distance between all of those solutions. Okay, from pi over 3 to pi, you've got 2/3 pi. From pi to 5/3 pi, that's 3/3, 4/3, 5/3, it's still 2/3 pi. And this was pi over 3, this was pi over 3, so you've got 2/3 pi again. So if we don't want to write 3 separate solutions, we can actually here combine them by starting with the first one, pi over 3, and then after that, we just have to add 2/3 pi. Any number of times to get to every spot that would land on that unit circle. Okay, if you don't see the patterns, you'll still have the correct 3 solutions. All that's happening is you're repeating yourself. You're going to land on the same solutions more than once. Okay, so we want to avoid that if we can. Not the biggest disaster if you don't see them right away. Last one, this is 52 over 100. I hope you can see that cosine theta is -52 over 100. I wrote it like that so you could very clearly see that that is not sides of a triangle that we know. Okay, so let's draw a picture and figure out where cosine's negative. Okay, that's going to help us with our process here. We've got second and third quadrant, and we just need to go find the inverse. Because it's not going to be nice, we're just going to use our calculator to find a solution for us. And if you want to change it back to your decimal, you're more than welcome to. Okay, so I've got approximately 2.12. Okay, but I should have 2 solutions, so I need to find my second one here. Now, for this one, we've got theta equals 2.12. That gets me all the way here. So in order to get to the other one, I've got to figure out how I can manage to do that based on what I just saw. Pause the video and think about how you would do that. If you remember what I told you about cosines, okay, in order to get it, when we saw it in the first quadrant, we used theta and then we took 2 pi minus theta. That works for cosine every single time. This is theta from here to here. If I want to get the backwards distance over here, I just take 2 pi minus theta. Can you see that this top distance here would be the same as this? And if I take 2 pi minus that 2.12, I actually end up there. Okay, so for cosine, we're taking the period minus theta to get the second solution. Okay, so we will take 2 pi and subtract that answer. So about 4.17. After that, we just need to add 2 pi in to get all of the possible solutions that we can have. Okay. If you have any questions on this video or struggle when you're doing the homework, be sure to come in and ask some questions.